Okay, we're going to be talking about the SAGE air defense system. And as I was preparing this talk, I had an idea. I was trying to understand why the acronym is SAGE and the expansion is the Semi-Automatic Ground Environment, which is a phrase that doesn't really describe what the system does. And I had a thought, and I think this is the case, but I don't have any factual evidence for this. But I think really they just wanted to call it the SAGE because it's the system that knows everything. And then they backfilled a phrase to come up with the letters SAGE. So let's talk about it. Really, the impetus for SAGE is that you have, in World War II, you have radar systems that a radar system, it sends out a radio wave. The radio wave reflects off something in the environment and comes back to the radar station. And by analyzing the reflected signal, you can determine distance and orientation of objects that are out there. And radar capabilities improved significantly during World War II. And here's an example of a World War II era radar station. So the return signal gets reflected back, and then that signal is electrically amplified and ends up being displayed on a CRT screen. They use a long persistence phosphor on the screen so that the screen will retain the image for a period of time, because the radar is not giving a continuous signal for all directions. It's scanning out into the environment, and then you get a scan signal that's displayed on the screen. And any information that comes out of the system is all recorded and tracked manually. So, either you're just saying it verbally to other people in the command center, whatever you're observing on the radar, or maybe you're only reporting back when some commanding officer says, "What do you see?" Or you're writing it down on a slip of paper that's, handed off to somebody else. The motivation for SAGE is that at the end of World War II, the United States is the only nuclear power, right? And there was a lot of concern about the Soviet Union obtaining the atomic bomb, which they do in August of 1949. So the test detonation that the Soviet Union did, this is detected and analyzed by scientists in the United States, and they realize that the Soviets have the bomb. It won't be announced to the general public until about a few weeks later in September. But at this time, there's no intercontinental ballistic missiles yet, so it's not a missile threat, it's a bomber threat. The Soviet Union having the atomic bomb represents a threat of an air attack coming across the northern pole of the Earth, across Canada, and into the United States. And so this is considered a very serious threat, and we need to do something about it. But all of our radar stations are all situated on the coast. There's nothing looking across the pole. So the response of the United States military is to form what they call the Air Defense Systems Engineering Committee. And if you read the history on this system, you're just going to see one acronym after another. And I'm not going to use all of them in this talk, but this is the first group of people that get together and they decide what they're going to do in response to this realization that an atomic bomb threat delivered by bombers from the North Pole, from the Soviet Union, is a very real thing. So what are they going to do about it? So George Valley proposes that they assemble a group of experts to analyze the needs of the Defense Department. And they form this committee, and they decide that the existing network of a few large radars and manual methods of processing and relaying the radar data is insufficient, because although it's not a matter of minutes like it is with a missile attack, it's still a limited amount of time between when bombers could be detected and any kind of response could be launched. So ADSEC recommends that they add a large number of smaller radars for greater coverage to fill the gaps between these large radars that they have. They're going to need communication lines between these systems to link them together. And they're going to need some kind of centralized automated system to handle all the information that's coming back from these distributed radar network. They need to do two things. They need to upgrade their existing systems as quickly as possible, and they need some kind of long-term solution for how to integrate this whole system to create a coordinated response. And remember, this is 1949, so computers are extremely primitive. But their recommendation is that the central system should be computerized to make it as automated as possible in terms of getting the information to the people that are going to make the decisions. So it's a command network and a control network in the sense that they're going to issue commands to, Air Force bases, to launch fighters and so on. So that's the control part, and the command part is receiving all this data so they can make an informed decision. So out of this initial advisory committee, they create something called Project Charles. And this is remember, it's 1949, so computers are extremely primitive. They're vacuum tube based. Nobody's built large computers before. Nobody's built a communication network to have computers talk to each other before. A whole bunch of problems need to be solved. So the first thing they need to do is to get basically the smart people together to figure out how they're even going to do this. So they form Project Charles, which is an air defense study group headed by F. Wheeler Loomis. They begin work on these recommendations. The existing systems are upgraded by, the existing systems being the existing radar installations that are on the coast. They're upgraded by Bell Labs and Western Electric, and a research laboratory is established to figure out what they're going to build for this long-term solution. The group that's put together to figure out the long-term solution involving computers is called Project Lincoln. This later becomes Lincoln Laboratory. It's associated with MIT, and that is established in 1951. I think it's only a year or two when it was called Project Lincoln, and it gets its name changed to Lincoln Laboratory. So the Lincoln Laboratory at MIT, they didn't invent everything from scratch. They drew on research from other laboratories at MIT. They also poached personnel. And their job is to integrate all these different ideas into a working prototype system. And they also have to write the initial control software. So there's a huge software suite that's going to have to be written to analyze all this incoming data, process it into some kind of form to present to decision makers in the form of some kind of display, and then relay communication results back out. This is what Lincoln Laboratory looks like in 1956. You can see it's got like a big kind of radar dome there on one of the buildings, and it's a fairly large place. So you can imagine there's a large number of people that are working on this project just at Lincoln Laboratory. The Digital Computer Laboratory at MIT had already been working on improving the reliability of vacuum tube-based computers. And nowadays we have little supercomputers in our pockets that they run for years and years and years and years and they don't break. But a vacuum tube computer is a very fussy beast. The vacuum tubes themselves have a limited lifetime. After a certain number of hours of just running the tube just starts to fail electrically. It may also fail mechanically in the sense of like losing the vacuum and then the circuitry doesn't work anymore. But one of the things that the Whirlwind computer was designed to address was the reliability of these vacuum tubes, which were one element of a whole computer system. Another element is the memory in an early computer. Very early computers use relays, mechanical relays for storing bits. That's very, very slow. So they started using something called a Williams tube, which is basically a CRT, and you spray electrons onto the screen of the CRT, and there's a way to read it back to find out whether you sprayed enough electrons to represent a 1-bit or a 0-bit. But even these memory devices are prone to failure, and they have a lot of fiddly little adjustments that have to be made all the time. So the reliability of the memory system is low. the reliability of the vacuum tubes to implement any kind of electronic circuit for digital computation, that is also low. So Project Whirlwind at MIT is an early prototype vacuum tube computer that is designed to explore how to get more reliable computers. And one of the things that they found is that if they just worked with the manufacturers of the vacuum tubes, they could actually, by changing the manufacturing process, they could increase the reliability of the tubes significantly. But the other big thing that they found out is that vacuum tubes don't fail all at once. They fail gradually, and this is just due to the way a vacuum tube circuit works. There's a bunch of grids. There's inside of the tube. The reason it's a vacuum tube is because the way the circuit works is by emitting electrons into the vacuum and then controlling the electrons with various grids to accelerate or decelerate them. And it's a crazy electromechanical device inside this little piece of glass. So they found out that what happens to the circuitry is due to all the interactions between the metals and the electrons, is that the things don't fail all at once. They fail gradually. And you can measure that gradual failure by measuring the response of the tube to various applied voltages to the internal components of the tube, and they call that marginal checking. So Project Whirlwind invents this process that they call marginal checking, where they can take a tube out, put it in a test fixture, apply test voltages to the tube, and then they can say with a fair amount of certainty, this tube hasn't failed yet, but it's going to fail soon. And by doing that, you can replace the tubes before they fail and keep a working system. Here's a picture from the Museum of Science in Boston. On the right, you see the racks of the Whirlwind computer. This is not the whole computer, by the way. This is just a chunk of it that fits in the picture. You can see the little CRT tubes there. Those are the tubes that are used for displaying this marginal checking voltages as they're checking these tubes. And on the left in that kind of vertical column that's lit up, that's the core memory portion of the Whirlwind, which we'll talk about a little bit later. Here's another picture of Whirlwind that gives you an idea of just how large the whole computer is. You can see it's spanning like in about 9 or 10 racks there. These are 19-inch, kind of standard 19-inch equipment racks. The 19-inch standard comes out of the telephone world, where they standardized on equipment sizes. Another laboratory that was used to feed into the SAGE project is the Cambridge Research Laboratory at Wright-Patterson Air Force Base. And they had developed a process called slowed down video, and this was a means whereby they could take the return signal of a radar installation, encode it in such a way that it could be transmitted over a phone line to another computer and then displayed on another monitor. So this gives you the ability to visualize the results of a radar installation without having to physically be at the radar installation. So long distance communication of digital images is, it's essentially a digital image. It's a computerized, it's a processed, computerized version of the return signal for a radar installation. They also developed some improved pre-processing on the radar signal to allow them to get improved target location. And they had this scheme for communicating, arbitrary digital data between two sites. And remember, this is early 50s, so nobody's figured out modems yet. That's not a thing. Nobody's figured out digital communication standards that's not a thing. There's not even digital standards at all, because everybody's making their own bespoke computer that's, fits their specific needs. There's not even an idea of like a general purpose computer yet that is widely available to do arbitrary tasks. So they put all this stuff together, pulling the ideas from these different laboratories, and they create a prototype system, what's called the Cape Cod system, in 1952. This is a small-scale demonstration system, but it has all the elements of the final SAGE system just in a reduced form. And it's called the Cape Cod system because they had a radar network, a group of radars deployed in the Cape Cod, Massachusetts area. And They wrote about 35,000 instructions for the control software for the Cape Cod system. So in its own right, it's a fairly significant software project for the time. It uses, it's one of the first systems to do time sharing, if not the first system to do time sharing. By time sharing, what we mean is there's a central computer that is serving multiple users simultaneously, and the multiple users are the operators looking at the displays for identifying aircraft tracks and friend or foe systems and so on. Each of those CRT displays is all serviced by a single central computer. There's not a computer per display like we would typically have now. There's a single central computer that's refreshing and updating all the displays and accepting the input from all the operators at all the displays. So they're getting a slice of time from the CPU, hence called time sharing. The computer used in this Cape Cod system is the Whirlwind computer itself. So it was already built and then just repurposed and used for this, which probably saved them a considerable amount of time because Project Whirlwind itself didn't appear overnight. But Whirlwind let them get a system up and running as a prototype and find out, what kind of additional problems they were going to need to solve. Here's some pictures of like the typical radars that were used in this Cape Cod system. On the left, you see this that dome contains a long-range radar, and then on the right, you see that picture of the building with a big, you've probably seen it in lots of movies, big rotating antennas that are emitting radio waves, and then the curved metal framework is receiving the reflection and focusing it to a point where there's a sensor that's analyzing the return signal. The typical display is just a big CRT tube with, simple vector graphics information that represents, the location of any aircraft in the air that they've identified. They might have a little tag on it that indicates whether it's a friendly aircraft or an enemy aircraft. And the input to the system, there's, of course, at the consoles, there's buttons and switches that they can use to indicate various single bits of input. But they also use a light gun. And I believe this is the first use of a light gun. A light gun, in later evolution of computer graphics, it would be referred to as a light pen. But a light gun is basically a sensor that can create an electric signal when presented with light. So when the computer scans the screen and draws something on the screen, that emits light. If you're holding the sensor in front of that part of the screen, the sensor detects the light and turns that back into a voltage. And if you are holding the trigger on the gun, then that voltage is sampled. And by correlating the refresh of the screen with the time at which the signal was detected from the light gun, they can identify what portion of the screen you're pointing at with the light gun. So this is basically a two-dimensional input device that allows you to have something on your screen. You can point the light gun at it, pull the trigger, and then the computer knows, oh, you're selecting this aircraft at this position on the screen. So now I've allowed you to graphically select something off the screen instead of just having to maybe get out like a ruler and measure its position on the screen and then type in some numbers. You can just directly select it visually. I think this is the first time that there was ever any kind of 2D input device into a computer. I mean, now we would use a mouse and there would be a cursor, would be the more modern way you would do it. But with this light gun, they can directly select things graphically and enter and give feedback into the system. The intercept room for the Cape Cod system is a slimmed down version of what would be ultimately deployed in the Sage system. And you can see all the operators here at their various consoles, and each operator has a different task. They're not necessarily all doing the same thing and not necessarily looking at all the same kind of displays. But they're in there together. They can communicate with each other, obviously verbally, because they're sitting right next to each other, but they're also communicating directly with the machine, the control software that's analyzing all this input data from the radar stations and then using the inputs from the operators to feed back into turn into what ultimately would be, information fed back to a command structure that would decide on what kind of response there was going to be if there was any kind of incoming attack. So from that Cape Cod system, they put together an idea of what the final system needs to be. It's going to be very similar to Whirlwind, but it's not going to be the Whirlwind CPU directly. They're gonna all this military stuff all has these crazy alphanumeric designators, right? So the computer itself is called the ANFSQ7. What ends up happening is it ends up getting jointly developed by Lincoln Laboratory and IBM, which I imagine has got to be a different experience for IBM, where usually IBM does the development, right, in-house completely. So here it's being jointly developed between an MIT research laboratory and IBM. It is a so-called duplex design, which means that everything in the CPU system is duplicated. And that is because they need to have a high reliability for this system. They can't have the computer just go down in the middle of a bomber attack, right? That's just not acceptable. So what they're going to have is two computers running continuously side by side, and if they're both executing the same code concurrently, and if the live system fails, it just switches over to the other system, and then you repair the system that failed and put it back online so that they're both executing the same code in parallel. So that gives you a hard failover to get redundancy, because you can't have the CPU fail in this system when you depend on it. So it's a so-called duplex system, and they're going to use this core memory that was developed for Whirlwind, which we'll talk about core memory in a second. And the reference that I was reading, it was a paper, an issue of IEEE Annals of Computing History, a special issue on the SAGE. They say that it's the first system to use random access core memory. And there might be, whenever you say anything about firsts in the vintage computing space, there's always somebody like, oh, I remember there was an older system. It's not really important, to nitpick on the first part. The thing is that the FSQ7 was the first machine that wasn't a research machine to use core memory. And core memory is inherently random access. It's not sequential access like drum memory. It's not sequential access like tape. And it's not sequential like cards, okay? So it's random access is the important part. There is auxiliary memory for this system that is stored on drums. So if you're not familiar with what drum memory is, it's just like what it sounds. It is a metal drum with a magnetic coating, and it spins around, and there are read heads that are positioned over the drum. And as the drum spins around, the bits fly under the read heads, and then you can read out what was stored there, or you can use the write head to replace what was stored there. But you have to wait for the drum to spin around for the data that you're interested in. It's similar to a hard disk, but it's just not organized as a platter, it's organized as a drum. Now, a big change from the Whirlwind computer, which had a single arithmetic unit, the ANFSQ7 has dual arithmetic units, so they can process X and Y coordinates in parallel. And that ends up being important. You might not think it's like, well, it's just two versus one. But you got to remember these computers are very slow compared to what we're used to today. So getting that little bit of parallelism by being able to process the X coordinate and the Y coordinate of these radar track data, that ends up being a really big boost for performance for this system. It also ends up being the largest discrete computer system ever built, and probably will hold that record until the end of time. Here's a picture of one of the racks that implements the CPU. And if you look carefully, you'll notice there's a phone at the end of that rack. That'll give you an idea of how big this computer is, that to talk to somebody else that's looking at another part of the computer, you need to get them on the phone. They're that far away. Okay, so as I mentioned, this core memory idea was invented for Project Whirlwind. And the idea, and here's a very close-up view, and if you look carefully, you can probably see these little silver donuts arranged in this grid, and then there's wires that are fed through the donuts in an XY pattern. and also a diagonal pattern. And this core memory is invented to replace the Williams tube memory that they were initially using on Project Whirlwind, but it was so unreliable they didn't deem it as a viable solution going forward. And the idea is you have a little magnet, and then by running a current wire through the center of the magnet, you can either polarize the magnet one direction, or you can polarize the magnet in the other direction. And this is how you store a bit. So each one of these little metal donuts is storing one single bit of information. Now, this picture is magnified that you're seeing. The donuts are really small. And the idea is that by using this, it's essentially the first solid state memory. Okay, so it's not using, electrons in a vacuum. That's not solid. That's, kind of, you could argue whether it's plasma or whether it's gas, but the first solid state memory, it ends up being very reliable because the magnets don't wear out, the wires don't wear out, but it does have this weird property that in order to read a bit from the memory, you actually destroy what was there when you read it. So every time you use core memory, you have this weird thing where you read it and then you immediately write the bit back that you just read in order to determine what was stored there. But because it's magnets, and magnets retain their polarity whether they're powered or not. In fact, it's not actually the magnets that are powered, it's the wires that run through the magnets that are powered. So it does have the nice property that when you turn the machine off, whatever was in the core memory remains. So you turn the machine back on, and it can just continue executing right from where it left off. There were a lot of mini computers in the 60s that exploited this fact for control systems. They had a power fail indicator. They would sense if the power was about to go out. It would invoke a special routine that would save off of whatever little information that was only in the registers. It would save that into the core memory, and then the machine would shut down. And then when the power came back on, the machine could just continue executing right from where it left off. As I mentioned, there's also these drum memories. Here you can see the drums themselves. They're fairly large, and they're spinning quite fast, but it's still slower than core memory because you won't get the information back in a predictable time because it has to wait for the drum to spin around to be under the read head and so on. The drums are divided into tracks, and the ANFSQ machine it's a 32-bit word, and there's 2048, so 2K words on a track. So not a lot by today's standards, but we're talking like 1950s here. So it's pretty impressive for the 1950s. So here's a few little factoids about the FSQ7. 49,000 vacuum tubes. And you can just imagine, if these vacuum tubes are not very reliable, how many of these 49,000 tubes are about to fail at any given moment? Which is why they have a duplex system, and using this system of marginal checking that was created for Whirlwind, and they're constantly got a crew of Air Force personnel that are always testing and measuring and monitoring all these 49,000 tubes and trying to replace them just before they fail, so that the system always stays working. Remember, it's not just the one system that's running that has to stay working. Both of the systems have to stay working because you might have to hot fail over from one machine to the other at any given moment. As I said, the machine is a 32-bit word machine, but they have two banks of core memory. In the literature, you might see it referred to as the big bank and the small bank. In reality, the banks were configurable, and different sites had different amounts of memory in the two banks. But the typical configuration was 64K words in the so-called big bank, and then 4K words in the so-called small bank. This thing takes 3 megawatts of electricity to stay running, and that's not a peak use. That's 24/7. Okay, and it weighs 250 tons, 500,000 pounds. The whole thing, they build what's called a direction center, and this is a 4-story complex. The ground floor has diesel generators, and cooling equipment. The second floor has the computer. We'll see a kind of a blow-up diagram of the building in a second. The third floor has all the personnel monitoring all the displays, and then the fourth floor has kind of a maintenance area and various other activities going on there. For peripheral equipment for this computer, remember the computer is made by IBM, so for standard things like, card punches and card readers and line printers, they're just using peripherals from IBM for that. 723 card punch, IBM names everything with numbers. A 713 card reader, a 718 line printer. There's these auxiliary drum memories. There are magnetic tape drives, IBM 728 drives. There's also this thing called a cross-telling input, and that is how the different Sage installations communicate with each other, because remember, the United States being, spanning 4 time zones and 4,000 miles wide, there's different air defense sectors, and there's a command unit for each sector, but they have to talk to each other so that they can understand what's going on in the big picture sense. So the Sage computer has these so-called cross-telling inputs, and that's basically information about flight tracks and other tracked information coming from other sites that's fed into the site that you're at. There's also this thing called the display and warning light system, which we'll talk about more in a second here. So here's, you can see this at the Computer History Museum. This is a picture of what is at the Computer History Museum in California. This is one of the consoles, and you'll notice, you'll notice that there's groups of switches and buttons, and you'll see in that little plastic case there's one of the light guns. What's that? On the left is at the edge of the picture. Okay, I'm not sure what Ian is talking about, but it doesn't matter. The point is, each of these different display consoles, they have different duties, different responsibilities for their part in analyzing the defense condition, right? So the banks of switches that are attached to the console, those are different for the different tasks that each operator has to perform. So you may see other pictures of these consoles, and there will be different groups of switches and buttons attached to either the left-hand side or the right-hand side. They often get referred to as wings. Are you talking about the cigarette lighter, Ian? That's right. Okay, so in the very bottom left of this picture, I don't know, it's hard to see in this particular picture, but there's a cigarette lighter holder and an ashtray, because this is the 1950s after all, and everybody smokes. And you don't want your operators leaving in the middle of an important condition to go have a smoke break. So, okay, so this console display, it's a vector display. Now, you might be used to vector displays now. Computer graphics is commonplace, but in 1953, a computer-drawn vector display, this was a brand new thing. People were used to radar displays, but they weren't used to any kind of a display that was drawn by a computer. Most organizations outside of the military couldn't even afford a computer, much less the bespoke custom circuitry that would be needed to drive a CRT display from the computer itself. So it's a vector display. So most displays now are raster, where you have a grid of pixels and you're scanning them out left to right, top to bottom. But that requires a lot of memory, and memory is expensive, ridiculously expensive at this time. So we're not going to do that. We're going to do what's called a vector display. Instead, what's stored is a list of coordinates in some memory that is read out. As those coordinates are read out, they are used to drive the deflection of an electron beam across the screen. So it is literally drawing beams of electrons onto the CRT screen as determined by this array of coordinates being fed to the display system. Now, the display system's being fed by those drum memories. And the drum memories, they're rotating continuously, so they don't spin up and spin down. They're continuously rotating, so it's basically a big circular buffer that's flying under these read heads continuously. That circular buffer, they're grabbing data out of that circular buffer and feeding it to the display system to drive the display. So the display is continuously refreshed from these spinning drum memories. And essentially the drum memory contains what we would refer to now as a display list, a list of commands that say, go to this position on the screen, start drawing from that position to this other position. Now stop drawing and go to a new position on the screen and start drawing again. So that's the main display, this big circular display that you can see here in the center. Now, just above and to the right of that circular display, you can barely see a little rectangular display. That is the so-called message display. The message display itself is an interesting beast because it uses something called a charactron tube. Again, remember, this is the 1950s, right? So everything is either very primitive or exceedingly ingenious. And the charactron tube is quite ingenious. What they have is a CRT tube. Inside the tube is a metal plate. That metal plate has the shapes of characters cut out of it like a stamp. And so what you do is you send a very fat electron beam, you position it on this XY grid that selects the character. This very fat electron beam goes through this grid. Now the electrons are literally in the shape of the character. And then they hit the screen and it draws the letter R, or whatever is supposed to be displayed. And that's the charactron tube. It's a super crazy invention. Like, we would never do things this way now. We would just draw pixels to write the R on the screen. And they're like, well, that's going to take too much crazy circuitry to draw an R with lines. That's just stupid. Why don't we just take the electron beam and shape it to look like an R and then blast that at the screen? I'm like, oh, that's a great idea. So this charactron tube off to the side that's used for displaying text messages, that's what they're using there. Here's just kind of a quick block diagram of the display subsystem. You can see the drums on top. They're constantly feeding this data. It goes through some processing blocks, and then it gets handed off to the display processor. By the way, all these details that for the technical details of the Sage, it's all been declassified. It's all on BitSaver's archive, and you can go read all these things in detail for yourself. Here's a close-up of the console light gun, which we haven't talked about. We haven't talked about the projection screen yet, but there's the console light gun and the projection screen pointer. The console light gun is on the left, and the projection screen pointer is on the right. We haven't talked about the projection screen. We will in a moment. So on the left there, that little metal tube has the sensor. Well, it has a sensor in the end of it, and that is fed through as a voltage to a photomultiplier tube, or I guess it's fed through optically. At any rate, there's a photomultiplier tube in the light gun that amplifies whatever small amount of photons that they're sensing off the screen, turns that into a voltage that's big enough they can be sent off to the console and transmitted back to the main system for determining a position on the screen. The input architecture for this console is, there's buttons and switches that are providing these discrete inputs, and as I say, the array of buttons and switches that you have is configured for the different tasks, so each console is customized for what task needs to be performed at it. The light gun gives you this 2D point input from the screen, and it uses the photoelectric effect to turn photons into an electrical signal that can be measured. As I explained earlier, the light gun, by correlating with a display refresh and the sensing of the photons on the screen at a moment in time, you can correlate those two the display refresh time and the measurement time to understand where the operator is pointing on the screen. Now here's a picture of the command post. The command post is above where all the individual console operators are. I think it's on the same floor, but what is above, you see there's that kind of hole in the ceiling, and that's where the projection is coming from. It's being projected onto that screen. Now they got the lights up so that you can take this picture, so you can't really see the projected image. Normally this room would be darkened so that you could see the projected image, and you might be thinking like, wait, projector, how do they project a computer image in 1953? And the answer is they use a movie projector. Inside the special console, there's a CRT screen that's showing the display that they want to project. It is filmed onto 35 millimeter film. That 35 millimeter film is advanced into an automated developing bath, and then that developed film is moved up onto the projector. So you have this system. Can you hold questions to the end, and we'll use the mic, and then people can hear your question. So they use this system, this crazy system it's got the computer display on the one end. That's crazy enough, and then they're imaging it on photographic film. That photographic film is going through an automated developing bath, and then it's coming up into a projector that's projecting this 6-8 foot wide image on a screen. And you might say, like, well, that sounds like it's going to take a long time from when the image is created to when I can see it. It takes about 6 seconds. So there's a 6-second delay between whatever's projected on the screen. 6 or 8 seconds. I might be a little bit off on that number. I'd have to look it up in the documentation again. But the point is, it's not too long of a delay, but it is a bit of a delay. So, but it's the only way that they can have an automated system that's going to show them this situation display, a big display that everybody can look at once. So here's a darkened room projection there of what that would look like. And if you look carefully, that's actually Cape Cod that's on the screen. This is not the Cape Cod system, that early prototype. They're just showing the Cape Cod air defense sector. So as I say, this is, a CRT exposes onto a film. The film gets automatically developed through a chemical bath, and then it is projected onto a screen. If you remember, we talked about this system of marginal checking to identify these vacuum tubes when they're going to fail or when they're about to fail. And since there's 49,000 tubes in this machine, we have to be constantly checking all the tubes to find out, which ones are going to need to be replaced before they fail. So the FSQ7 has what's called this duplex maintenance console, and this is basically a giant physical test fixture for the electrical characteristics of the tubes that are in this machine. So you can imagine there's a crew of Air Force personnel, and they're constantly taking tubes out and measuring them and determining how close they are to failure. And if they're getting close to failure, then they're replaced. And this is just one portion of the maintenance console. This is not the entire maintenance console, because as you might imagine, there's a bunch of different kinds of tubes in the system. You want to be able to be testing tubes in parallel so you're not backlogged on a single testing station. So there's different portions of the maintenance console that are devoted to testing the different kinds of equipment that's in this system so that we achieve the necessary uptime, right? Here's a blowout of the 4 floors of what's called a direction center. There are other centers in the system. There are chunks of computing equipment at every radar installation that do pre-processing on the radar signal in order to condense it down and transmit it over the phone line. Remember, when I say transmit it over the phone line, you might think, yeah, I remember dialing up to the internet at 14.4K. No, this is like 300 baud would be awesome for what they're doing, right? Even though they're dedicated phone line circuits that they're getting from the phone company, it's a very low baud rate that they're transmitting these signals across. So the pre-processing on the signal is important to get it down to the essential information to transmit that to the central direction, what's called the direction center. And this basically, block diagram, you can just imagine that second floor in there where the computer is. Let's see, I think I might have a blow up of the second floor alone later. But that's the second floor where the computer is. We saw how big that rack was, right? It had a phone at the end. There's a guy standing there. The rack is like 8 feet tall. And there's like 8 of these racks across the entire floor. And they're, multiple racks deep. So it's a big, big place. So what's the deployment timeline for this? So in 54, the production contract is awarded to IBM. So remember, this is after they've done the experiment with the Cape Cod system using Whirlwind. So the production contract for the AN/FSQ7 CPU is awarded to IBM in 54. In 1955, a simplex computer, so it means just one, you have the duplex design, it's installed at Lincoln Laboratories by IBM so that Lincoln Laboratory can begin preparing the system software that's going to run this thing. In 1956, the first production AN/FSQ7 is accepted in what they call a test cell. So this is basically, they get the initial AN/FSQ7. There's probably minor engineering iterations that go through the system to improve the design or whatever flaws they might find while they're working with it at Lincoln Laboratories. And then the first production model is accepted a year later into a test cell. The test cell is basically just where they're going to continue developing the system integration of all the radar inputs and the peripheral devices and all the software that's going to be needed to run all this stuff. And then in 1958, 2 years later, the first directional center is operational. So you got to imagine, 55 or 56, they're already beginning to build this giant concrete 4-story structure that's going to hold this thing, right? You can't get the computer and then say, okay, now let's start building the building. They're doing all this stuff in parallel because they're trying to get this system as operational as quickly as possible. And then after the first directional center is operational, by 63, they have full deployment to 23 air defense sectors. So these are, each sector covers some geographic region of the United States, and Canada ends up being included as well. I haven't really talked about the radar installations that need to come online to support all of this, but you might have heard of something called the DEW line, the Distant Early Warning Line of radar stations. This is an array of radar stations across northern Canada, and this is the first set of radars that are going to be detecting any attack coming over the pole. Those radar stations are feeding all their data down into SAGE at the different defense sectors. In 1983, there were still 6 SAGE systems running, but by the end of, or by January of 84, all of the SAGE systems have been shut down. So this system runs for a good 30 years, right? And you gotta imagine, it's running for 30 years. What does that mean? Well, it means 2 CPUs are running 24 hours a day, 7 days a week, 365 days a year for 30 years. So that's a significant achievement to have a system running that long continuously. Let's talk a little bit about the software. The initial software for the Cape Cod system was 35,000 instructions. And you might think, what? It doesn't sound like a whole lot by today's standards, but you got to remember, back then, they had to write their own tools in order to take whatever their intellectual conception was of what the software needed to do and turn that into machine code. You couldn't buy a compiler. You couldn't buy an assembler. They were creating their own instruction set from scratch, so any tools that they were going to use, they had to create themselves. And you're not going to write 35,000 lines of machine code as hex digits. You just go insane, right? So they have to create their own tools first just to be able to create the software that they need. So in many ways, they're creating the first set of software development tools that ever existed because they had no other choice. Nobody written a piece of control software this large before. So a lot of the modern ideas of software engineering, they were invented out of necessity by the staff operating at either Lincoln Laboratories, where a lot of the initial software was written, or when it's transferred over to a separate group, because it's no longer a research project, and Lincoln Laboratory is nominally a research laboratory. It's not a production laboratory. So there's a point where the software development is transferred over to another group, and it's put in charge of, basically it's the Air Force that is running things at that point. The final system, just the control software, that runs is about 100,000 instructions. And you include all the other stuff that you have to have in order to keep this system maintained and operating, and doing, integrating new equipment. New missiles are coming online, new radars are coming online. Those new systems have to be continuously integrated into the SAGE because it has to understand everything and provide a coordinated response. So and the thing ran for 30 years. You didn't think we were using 1950s radar sets in the 80s. We were using 1980s radar sets. All those things have to be updated and integrated into the system, and that, as you know, involves software changes. So in the end, they end up with about 500,000 instructions if you include all the other stuff that they had to write to get the system running. This required a disciplined software engineering approach. Software engineering wasn't even a term, but everybody was an engineer that worked on this project. They needed to have a disciplined set of people that understood a certain way of thinking to stay organized and stay on track. You can't have somebody that's, I'm just a really creative guy and I want to do things my way. Your project would just die if you did it that way. Everybody, it's not that it was that there was no creativity involved, but it had to be disciplined. You had to have enough self-discipline to say, well, I'm going to create a specific interface for my piece of the system, and I'm going to document that well, and I'm going to explain it to the other people that have to use it so that they don't have to reverse engineer my code in order to write their code. And that discipline has to be extended all the way through the whole system. So they have to, have a rationalized approach. It's, people think of top-down engineering, software engineering as, sometimes it's characterized as a so-called big design up front, where you have this massive, elaborate specification, and then you just code to the specification. They did have massive amounts of specifications, but those specifications were created to document the results of their iterative development. So they actually, although they had big specifications that defined the whole system, they didn't write those specifications without having written code first to understand, well, this is how the code is going to work, and so I'm going to document it, and that's my specification, as opposed to just writing a document first and pretending that the document is perfect, and then I'm going to go write the code. They wrote the specification from their experience of creating the software, and they did have independent testing of their software at the different phases of development. I think that was something. This was probably an approach they adopted because they were used to testing all the electrical components of the system, the mechanical components of the system. So they thought, well, the software is just another component of the system, so we're going to rigorously test that as we go as well, because that's what we do. And as I said, they had to create their own tools to help build the pieces of the software that were going to be operational. And they had to, I think this is the first time that anybody was creating essentially a bug database. So anytime anything went wrong with the software, they had to dutifully record everything that went wrong and also what they did to fix it. And they kept that as a history of the evolution of the software, so that if something failed later, they could go back and say, oh, well, this new failure is a consequence of the previous fix that we applied that we didn't understand. It was going to have this distant effect over here. So the legacy of the FSQ is this core memory that was developed for Whirlwind and deployed in the FSQ7. This is used throughout mini computers and mainframe computers in the 60s and 70s and on. The core memory lasts all the way until you get a viable semiconductor memory replacement, so-called MOS memory or CMOS memory. And so it has a good run, core memory. The rigorous software development methodology that they created influenced subsequent large projects. And I haven't mentioned it at all, but the Sage software, one of the first commercial offshoots of the Sage software system, was a so-called Sabre system that was used to automate booking of airline flights. Because if you think about booking travel flights on airlines, it's basically the same coordinated problem as understanding a big array of, friend or foe planes that you need to track. Another first is that this cooperation between academic laboratories and commercial vendors, it established the ability to create large systems without giving everything to one vendor. I think that it's wise to have different groups cooperating, because you're going to get different insights from different groups. And if you give everything to one group, you're going to get something that looks like only the thinking that's within that one group. If you're a Linux user, you might have seen the phrase core dumped when your program crashes. And that is a legacy of core memory. When the program crashes and it says core dumped, what it's saying is, I've taken the contents of the core memory that was used by your program and I've written it out to a file. And even though we don't use core memory anymore, that phrase core dumped persists and is part of the hacker lexicon at this point. The maintenance consoles are full of blinky lights, and Hollywood loves blinky lights when they're going to make a sci-fi production or some kind of thing like that. And so in the 1960s, chunks of the Sage maintenance console appear, as props in Lost in Space. This is not an exhaustive list. I'm just kind of giving you a snapshot of one appearance throughout the decades. In the 70s, it appears in the Planet of the Apes TV show. In the 80s, it appears in a Get Smart movie. Among many other things, I'm picking examples where the maintenance console is prominently displayed here. 1994, a movie called Open Fire. Who knows what the plot line? I don't know this plot line of this particular movie, but that console looks pretty damn impressive in the back there. It even appears in the TV show Lost when they're in that hatch down in the underground. In the background is chunks of the Sage maintenance console blinking away. Of course, all the original electronics have all been stripped out, and it's just filled in with electronics. It just makes all the lights blink. Supergirl in 2016, still chunks of the maintenance console appearing in the back because it just looks cool. Agents of S.H.I.E.L.D., maintenance console appearing in the back there. So if you want to learn more about Whirlwind and the development of core memory, the development of the Sage, there's an excellent book called From Whirlwind to MITRE, the R&D story of the Sage Air Defense Computer. If you don't want to spend money, you can read all the technical documentation, of which there are many, many PDFs out on BitSavers. There's also an issue of IEEE Annals of the History of Computing, if I get the title correctly, I believe, for which I sourced a bunch of the specific facts that I've reported in this presentation. Mike Lowen, he's not here this year, but he's been here previous years. He was in the Air Force, programmed on the Sage in the 80s on the last installation before it was shut down. And he has a lot of pictures of pieces of Sage equipment and a lot more moving TV appearances on his website. Now that you've seen it, you're going to watch a TV show or a movie and you're like, I know what that is. That's a piece of the Sage duplex maintenance console. Unfortunately, although the CPU instruction set is well documented, we don't yet have an emulator. Maybe one of you will write one. We have enough information to write one, we just haven't gotten one yet. And with that, I thank you. I've used up all the time, so if you have questions, just come see me after. Oh, one little bit. Joe over here brought in one of the little tube units in the radar processor. You should probably just come grab these.